Okay, going on to section 1.3, here is a typical augmented matrix after reduction to reduced echelon form. So originally we had 6 unknowns and 5 equations, and we reduced it down, and we end up with 3 non-zero rows. So the first thing you do is, if you have any 0 rows at the bottom, those had better be zeros there also. Otherwise you have 0 equals something non-zero and there's no solution. So if you look at the 0 rows, if there's a non-zero in the right hand side, then you just say there's no solution and that's the end of it. It's called an inconsistent system. But assuming that all rows of zeros also have zeros there also, then that's a consistent system and there are solutions. And how many solutions are there? Well, let's define M to be the number of rows in the original matrix, that would be 5 here, and N be the number of columns in the original matrix, that would be 6. We're not counting this right hand side. And R is the number of non-zero rows after reduction to reduced echelon form. That's going to be called the rank later. So the number of non-zero rows after reduction, we're not counting these here, the non-zero rows in the matrix itself. Then you see you have these 3 unknowns, x1, x3, and x5, that are solved in terms of arbitrary variables x2, x4, and x6. And so there'll be 3 arbitrary constants, x2, x4, and x6. x1, x3, and x5 are solved in terms of those. So there'll be a total of 3 arbitrary constants. You could say it's like a 3-dimensional solution space because there's 3 independent variables that are arbitrary. And but notice that the total number of arbitrary variables is going to be n, the number of columns, minus r, because r is the number of non-zero rows in the final matrix. That'll be the number of not arbitrary variables. So the other n minus r are arbitrary. So n minus r is the total number of arbitrary variables, where n is the number of columns, that is the number of unknowns, and r is the rank, the number of non-zero rows after reduction down. Okay, here's another example. We have 6 equations originally in 7 unknowns, and after reduction to reduced row echelon form we have 4 non-zero rows. So r, the rank, would be 4. M, the number of original equations, is 6. N, the number of unknowns, is 7. And so how many arbitrary constants are there in the solution? Well, first of all, we're assuming that these 2 b's are 0. If either of these last 2 b's is non-zero, there's no solution. That's the end of the story. But assuming those are also 0, then how many arbitrary constants are there? There'll be n minus r, total number of variables minus the ones that are solved for. So there's 7 minus 4, i.e. 3, namely x2, x4, and x7 are the arbitrary variables. x1, x3, x5, and x6 are solved for in terms of those. Now, most of your homework problems in 1.3 are similar to these 4 problems here. Ignore the last 3. We haven't talked about independence yet. They're similar to this. They give you the number of equations, number of unknowns, and the number of non-zero rows in the final matrix. And you're supposed to tell whether there are many solutions, no solutions, or a unique solution, or what are the options. Well, if b is 0, that means the right-hand side is all zeros, then they'll stay 0, and that means that no solution is out of the question. There's guaranteed to be either unique solution or many solutions. And how many arbitrary constants are there? There's 7 minus 2, n minus r, that's 5. So there's going to be many solutions with 5 arbitrary variables. And the second problem, we have 7 by 3 matrix, and when you reduce it down there are 3 rows left, and there could be, the last 4 rows could have a right hand side that's not 0, so there could be no solution. But if the last 4 b's are all zeros. See, we didn't say we started with zeros, so we may not end with zeros. So assuming there are solutions, then there's got to be a unique solution, because the number of arbitrary variables is 3 minus 3 is 0. So if there are solutions, they'll be unique. And here it's the same thing, but now the right-hand side is 0, so it's guaranteed there'll be some solutions. 0, 0, 0 will always be a solution. So there's guaranteed to be a unique solution. It's only difference between this is the right-hand side is not necessarily 0, so you could end up with a right-hand side of 0 and rows of 0 on the left-hand side. But here that can't happen, because you start with zeros, you're going to end with zeros. And again, you've got n minus r, which is 3 minus 3 arbitrary constants. That's 0. So no arbitrary constants, the solution's unique. And finally, 6 equations, 5 unknowns. When you reduce it down, you have 4 non-zero equations. So there could be no solution if one of the last 2 b's is non-zero, but assuming that doesn't happen, if it's consistent, then there'll be 5 minus 4, which is 1 arbitrary constant, so there'll be many solutions. So there'll either be no solution. If there's any solution, there's one arbitrary variable. Going back to this example, I forgot to mention that the rank, the number of non-zero rows in reduced form, has got to be obviously less than m, because the number of rows after getting rid of 0 rows has got to be less than or equal to the number of rows total. But it's also less than n. You can't have more of these ones here than you have columns. There's at most 1 per column. 4 of the 7 columns have the ones in them. So r can't be more than m or n, so it's going to be less than or equal to the minimum of those. That's important in some of the homework problems. Actually, in most of your homework problems, they tell you what m and n are, but not r. But you have to remember that r can't be more than m or n, and take in all possibilities and tell what the possible outcomes are. For example, you have a homogeneous system. That means the right-hand side 0, so that rules out no solution. There's always going to be the 0 solution. If right-hand side 0, you can't have 0 equals non-zero. So, but you have 4 equations and 5 unknowns. Well, what's r? It doesn't tell you, but it's got to be less than 4 and less than 5, so it's less than or equal to 4. And so the total number of arbitrary constants is 5 minus r, and r is at most 4, so 5 minus r is at least 1, so there's at least 1 arbitrary constant, so there's many solutions. This problem, the homogeneous system of 3 equations and 3 unknowns, well, r is less than or equal to 3. If r is equal to 3, there'll be a unique solution, because there'll be 3 minus 3, 0 arbitrary constants. If r is less than 3, you'll end up with a row of zeros, and you'll have many solutions with at least 1 arbitrary constant. I gave you one problem in section 1.4. This is applications. That's problem 2. Let's look at problem 1, which is very much like it. It's a traffic configuration here. These are intersections, and these are roads. And there's 400 vehicles per hour coming in this way, 800 coming in this way, 600 going out that way, 400 going out that way, so forth. And we're trying to calculate how many are going this way on that street. The arrow tells you the direction. If x turns out to be negative, it means it's really going the opposite direction, but we kind of arbitrarily decide that x1 positive means going that way, x1 negative is going the other way. So you've got 4 unknowns, x1, x2, x3, and x4, the traffic on each of these 4 roads. Those are the unknowns. You got 4 equations by balancing the traffic coming into each intersection with that going out. So x1 plus x4, which is going out, is equal to 800 plus 400, which is 1200. So x1 plus x4 is 1200. Do the same thing at each of these 4 intersections, and you get 4 equations for 4 unknowns. And here are the equations. Like at the first intersection, as we said, x1 plus x4 has to add up to the number coming in, which is 1200, x1 plus x2, and the next intersection has to add up to the number going out or in, forget, with 1000, and so forth. So there's the 4 equations. Now, I said earlier that in the real world applications, you nearly always have same number of equations as unknowns, and you nearly always have a unique solution. Well, here's an example where you don't have a unique solution, because you reduce this down to echelon form. You take -1 times this and add it to the second. There's not much work to do here because mostly zeros below the diagonal anyway and above. So just all you have to do is take -1 times the first equation, add it to the second. Then you take -1 times the second equation, add it to the third, and -1 times third equation, add it to the fourth. And this is what you end up with. And notice you came out with a 0 here. And we'll see why that's a 0. Did we just get lucky? Well, sort of, but we did get lucky. So you basically just ignore that last equation. And x4 is arbitrary, so we could solve for x1, x2, and x3 in terms of the arbitrary variable x4. x1 is equal to 1200 minus x4. x2 is minus 200 plus x4. x3 is 600 minus x4. But x4 is completely arbitrary. And if all of, it says if x4 is 100, what are the others? Well, you just plug in x4 and you'll get x1 is 1100, x2 is minus 100, means it's going the opposite direction indicated, x3 is 500. And what's the, so x4 has, if all the x's are positive, if they're all going in the direction that's shown, if those are really one-way streets, then x4 has to be at least 200 to make that positive, but it can't be more than 600 or that will go negative. So if we insist that all the x's are positive, those are one-way streets, then x4 has to be between 200 and 600. Now, so did we get lucky that there is a solution? Well, sort of, because you can show that if the total number of cars per hour coming in, that'd be 400 plus 800, and then plus 200 plus 200, that's 1600. Got to be the total number going out, which is 400 plus 600, that's 1000 plus 600, 1600. So the total number of cars coming in balances the total number coming out. Otherwise, if there are more cars coming in than going out, then the traffic flow in these things can't be constant. It's going to be steadily increasing or decreasing. So that's why we were able to get a solution, but it's not, it's not unique.